Hello class, welcome to today's lecture on energy balances in environmental engineering. Before we dive into the content, let's outline our learning objectives and discuss why this topic is crucial in the field. By the end of this lecture, you should be able to describe the first law of thermodynamics and its components, describe the main components of an energy balance, define enthalpy and the associated concepts of specific heat and phase change, define the second law of thermodynamics and the relationship between energy transformation, and describe the mechanisms of heat transfer. All of these are embedded in some examples where you will apply energy balances to the context of environmental issues and sustainability. So understanding energy balance is fundamental to environmental engineering to several key reasons. Modern society depends on energy, and our daily lives and economic activities heavily rely on energy. So consider how petroleum industry enables numerous aspects of modern living and the global economy. In the area of energy transformations, for example, meeting society's energy needs involves complex transformations and control of energy flows. So as environmental engineers, we must understand these processes to manage them efficiently and minimize negative environmental impacts. Another important aspect of energy balance is the environmental consequences associated to the energy. For example, energy production and use, especially from fossil fuels, significantly contribute to environmental problems. So did you know that the energy sector accounts for about 3/4 of global greenhouse gas emissions? The other issue that we have is more local. Energy loss and inefficiencies can lead to localized problems such as heat pollution, affecting local ecosystems and water bodies. And then we also have environmental impacts at global scale. For example, the overlooked and underappreciated climate change, ocean acidification, and sea level rise, which are enhanced by greenhouse gas emissions from the energy industry. Energy balances are also fundamental to controlling processing operations, particularly in managing product yields and reducing energy consumption in industries. So during this lecture and the tutorial session, we're going to cover examples related to global warming because it is a thermodynamic problem, and it occurs, for example, on alterations due to the global energy balance, excessive use of energy due to inefficient energy conservation, greenhouse gas pollutants and changes in albedo, and excessive waste heat from human activities due to inefficient energy systems. So we're going to talk about, for example, the coal fuel industry and how is this related to the waste of energy, and the waste of energy, how it is related to the global warming. Now let's start understanding the first concepts of core concepts of energy balances that you may be familiar with from previous courses. And we're going to start with the first law of thermodynamics. The first law of thermodynamics states that the energy can neither be created nor destroyed, only converted from one form to another. To apply the first law, we must define the system being studied by drawing an imaginary boundary around it. This system can be anything, from an engine, like in a car, to the earth itself. The area outside this boundary is called the surroundings. Systems are classified as either open or closed, where open systems have flows of both energy and matter, and closed systems are systems where only energy can flow across the boundary, not matter. For any defined system, we can write an energy balance equation. And the general balance equations is energy in minus energy out plus energy generated minus energy consumed equals the change of energy of the system. In closed systems, the terms related to mass movement across the boundary are eliminated. The terms related to the energy generation or the energy consumption are related to work and heat transfer, where heat transfer can be done due to a change in temperature, and work can be done from an application of work from the surroundings that we will explain later. As you can see, the terms Q and W can have a positive sign or a negative sign, and this will depend on if it's been applied into the system or it's been taken from the system. Now let's take a closer look to the internal energy or the accumulation of energy that may be due to microscopic changes and microscopic changes. The total energy of a substance can be described as the sum of its internal energy, U, the kinetic energy, Ke, and potential energy, Pe. This equation helps us to account for all forms of energy in a system, including the microscopic forms related to molecular structure and macroscopic forms, like the observable kinetic and potential energies. In many applications of our energy balance equation, the net energy added to a system will cause an increase in temperature. For instance, wastewater from a coal-fired plant will increase the temperature of a river where it is discharged. The amount of energy needed to raise the temperature of a unit mass of a substance by 1 degree is called the specific heat, and we're gonna discuss this more in detail on the following slides. This concept is crucial in understanding how different materials respond to energy inputs. But for most applications, the specific heat of a liquid or solid can be treated as a simple quantity that varies slightly with temperature. So we have, however, two cases. We're going to divide the ones that are that have an effect only on the temperature, and the others that are related, for example, to gases, where there is going to be a change in volume. To handle systems that change pressure and volume, we introduce another thermodynamic property called enthalpy. The enthalpy of a substance is defined as H equals internal energy plus a change of pressure and volume. Enthalpy of a unit mass of a substance will depend on its temperature and has energy units. Enthalpy is a state function, meaning that it depends only on the current state of the system, temperature, pressure, and composition, and not on how the system arrived at that state. So generally, we will use delta enthalpy instead of only H. We use it because we are not using absolute values. We're using the rate of change in related to a reference value. So we use delta H because it is directly corresponding to a way of measuring heat transfer at a constant pressure, and it provides a baseline for many transformations that deliver a change of energy. So when a process occurs without a change of volume, the relationship between internal energy and temperature change is given by the first equation. So as you can see, we still conserving or maintaining the delta U. And then similarly, we're gonna have another equation, but this is at constant pressure. So that's why Cp is the specific heat or at constant pressure. It's we define it as in this form, and then we will have an equation that will have a description of the change of internal energy. For many environmental systems, the substances heated are solids or liquids, and then we can have no distinction between if it's a heat capacity at constant volume or heat capacity at constant pressure. So we can write the general form as mc delta T, okay? So the specific heat capacities of common substances can be found in tables, and here we can show, I'm showing you the specific heat capacities of common substances such as air, steel, water, etc. And then you can observe something that is very interesting. The heat capacity, specific heat capacity of the water is way much higher than other substances. And now you can understand more the relationship of the capacity of the oceans to absorb energy, and also the changes of energy or temperature variations in, for example, coastal areas. And this is also key to understand climate change and also the overall temperature of the planet, how it's regulated due to this property, right? But on the other hand, we can also see the heat capacity of other materials that is very, very low. So you can observe the specific heat capacity of the copper, and that is why it may not be a useful material for making, or the metals in general are not useful materials for making houses, right, or homes, because they will not maintain the temperature, or they will not regulate the temperature, right? It's interesting also to see that we also have a specific heat capacity, the human body, and yeah, also there is a specific heat capacity of materials that are commonly used in buildings, and also air and other materials, right? So now we're going to discuss a specific case of the change or the enthalpy, and is what happens when there is a change of phase. And this is called latent heat. So examples that we can mention is for when ice melts into water or water boils into steam. In these cases, energy is absorbed or released without any change in temperature. So this is where latent heat comes into play, okay? The latent heat of fusion, or enthalpy of fusion, is the energy required to change one unit of mass from solid to liquid at constant pressure. So in the figure, what I'm showing you is the heat added to 1 kilogram of ice, and then on the left side, on the y-axis, is the temperature, and here you can see the transformations of the water and the energy that has been required or added, okay? Then I'm showing you in the right side a more simplified figure that is the same as the one on the left, but what I wanted to show you is that the energy, the heat added, is Q, and I can also provide you the distinction between sensible and latent heat. And you can clearly see that with sensible heat, there is a change in temperature, where when we have latent heat, there is no change in temperature, but there is a change of phase. So we have some numbers here. For example, to melt 1 kilogram of ice into water at 0 degrees Celsius, we need 334 kilojoules of energy. And to convert 1 kilogram of water at 100 degrees Celsius into steam, you need 2260 kilojoules of energy. So now there is something here very interesting. When steam condenses back into water, or when water freezes into ice, those exact amounts of energy are released back into the environment. And we're going to have an example, a very interesting example during the tutorial about the amount of energy that is required to evaporate the water of the liquid water in the planet. Here I'm showing you in the bottom of the right figure the equations of the latent heat and the equation of the sensible heat. Latent heat is the energy absorbed or release of a substance during a phase change, as we discussed before, right? And it doesn't have a change in temperature. The equation is Q equals mL, where L is the latent heat, and you can already predict the units because Q has energy units, for example, joules. This means that the latent heat should have units of joules per kilogram. So kilograms can be cancelled with the mass, right? M, as we said before, is the mass. And this, the form of the equation where there is a change in temperature is the sensible heat. And then you can already distinguish the change in units, right? In the term of CP, right? That should have the energy divided by the mass and the temperature, right? So the temperature units can be cancelled. So let's start our first example that is related to the Antarctic ice sheet. The Antarctic ice sheet is the largest single mass of ice on Earth. It has an average area of almost 14 million square kilometers and contains 26.5 million cubic kilometers of ice. This is the updated value of the change of the loss of ice mass in the Antarctica, and it has been taken from the website of the NASA. It loses mass of ice at a rate of 270 billion tons per year. So we're going to estimate what is the energy required to melt this amount of ice every year, and we're going to provide it in units of terawatts. We need to have a starting point to visualize, as in the figure that we had before, the change of the phase or the sensible heat, right? So we're going to start from assuming that the ice temperature is minus 20 degrees. And from there, remember that we will need energy required for change of temperature and then energy required for a change of phase, all right? So you know already that we need to calculate first the change of temperature because we need to have a change from minus 20 degrees to 0 degrees, right? And then from the at constant temperature, then we will calculate the latent heat, okay? So something that is going to be a little bit tricky in this problem is the use of the change of units. In environmental phenomena, we use very big numbers in general, right? So we are using terawatts here. Watts, remember that it's has units of joules per second. So it's a flow of energy, all right? And we will need to convert this flow of energy. We will need to transform this to terawatts hour. Well, from terawatt hours to average terawatts, okay? And to put it into perspective, it is very important to have something, a reference, right? So we're gonna compare this value that we obtain with the global energy produced by coal power plants, and so we can have a comparison of the amount of energy that has been required for melting these ice caps that probably in the future we will not have anymore. We're going to now discuss the second law of thermodynamics, and this is an important concept in environmental engineering. So let's break it down step by step, and just keep in mind that we're just targeting the general concepts of energy balances applied for environmental engineering, and we're not going into details that can be discussed in a thermodynamics lecture, for example. First, what is the second law of thermodynamics? Well, simply it deals with the direction of natural processes. Many processes in nature only happen in one direction, and we call these irreversible processes. Some examples are drop a glass, it breaks, so the broken pieces don't come back together on their own. Or heat always moves from hot things to cold things, and never the other way around. This example shows that some things in nature only happen one way. The second law of thermodynamics explains why. So we're going to see the example of a machine that uses heat to do work. For example, car engines. And so they take heat from a hot place, use some of it to do work, and release the rest to a cold place. Here's an important point. No heat engine can turn all the heat it receives into work. So there are no 100% efficient machines. So it means that some heat always gets lost to the surroundings. And so now let's look at the math behind. The work done by the engine, which is defined as W, equals the heat it takes in minus the heat it releases, which is QC. We can write this now as an equation, W equals QH minus QC. Now let's talk about efficiency. Efficiency tells us how well the engine turns heat into work. We calculate it like this. Efficiency, work done, heat taken in, or in math terms, efficiency equals W divided by QH. We can also write it as QH minus QC all divided by QH, or 1 minus QC divided by QH. Overall, we can also measure efficiency in terms of temperature. So then it means that N equals 1 minus Tc divided by Th. So in the figure on the right side, I can show you the representation of the heat transfer, where in the left side is like kind of the all the temperature or the energy is lost to the environment, whereas in an engine, a heat engine, we have some of the work, the energy used for work. All right. Understanding the second law of thermodynamics helps us to design better, more efficient systems. And this is crucial in environmental engineering. So, because you know that waste energy in systems will represent a bigger amount of fuels, for example, that need to be added into the system, but it also will imply heat pollution, and may also imply that heat that is lost is connected to carbon dioxide emissions when we're talking about fossil fuel energy, for example. These simple equations can help us to understand the efficiency in thermal power plants. For example, the one that is in this diagram. In this plant, fuel is burned in a fiery chamber surrounded by metal tubing. Water circulating through this boiling tubing is converted to high pressure, high temperature steam. During this conversion of chemical to thermal energy, losses on the order of 10% occur due to incomplete combustion and loss of heat up to the smokestack. Later we can consider the air pollution associated to these plants. because this is one of the primary problems for global warming. The steam produced in the boiler then enters a steam turbine. The high pressure steam expands as it passes through the turbine blades, causing a shaft that is connected to the generator to spin. The turbine shown in the picture is shown as a single unit, but it actually is a series of turbines that have many stages, with steam existing one stage and entering another, and gradually expanding and cooling as it goes. The generator converts the rotational energy of a spinning shaft into electrical power that goes out into transmission lines and also the distribution. So overall, throughout the passes of energy in all the system until the lines, the electricity lines, there is some loss of energy, the loss of energy that we have described before. In general, we know that for every 3 units of energy entering the average thermal power plant, approximately 1 unit is converted to electricity and 2 units are rejected to the environment as waste heat. And it's interesting to see that it's still happening in these times. So it has an improvements of energy, of efficiencies are very difficult to increase. So we can see this here on the right side, an example. If we state a reasonable temperature of steam that is around 600 degrees Celsius, and we know that the ambient temperature is about 20 degrees, we can estimate the efficiency, and it is about 66%, which correlates with what we were mentioning before. Now let's look at the efficiency of coal-fired power plants in Australia. This is an important topic for environmental engineers here because the majority of the energy obtained, a significant piece of energy that is being obtained in Australia or that is sourced, comes from these plants. I have not provided specific efficiency values, but what I can tell you in general is that older plants have a lower efficiency as compared to newer plants, as we explained before. And the most efficient power plant is the Tarong North, and it has a 39% of efficiency. Now, efficiency is important because it's connected to carbon dioxide emissions. So this is an important component for region of the emissions that occur in New South Wales and Victoria, only because they have the concentration of power plants, and also Queensland. It is worth mentioning that the largest power station in Australia is Loy Yang in Victoria and has a capacity of energy of 3,200 megawatts. We're going to use this power plant as an example for our next problem. We're gonna use this energy capacity of the coal-fired power plant in Loy Yang, Victoria, to estimate the energy that is transferred to the environment, considering an efficiency of the plant of 38%. And we're gonna also calculate how much CO2 is emitted to the atmosphere every year due only to the energy that is being wasted. And this is something very important because in many cases we talk about emissions or the offset of carbon dioxide emissions by only shutting down these sources of energy. That is almost impossible in many cases because we have communities and we have cities that depend on this energy. But by improving the efficiency, actually we could reduce already some greenhouse gas emissions associated to these power plants. We're going to start discussing the last topic of energy balances, which is heat transfer, that can occur due to conduction, convection and radiation. Some examples that we are going to discuss in this section is energy crossing boundaries, which is highly important to understand insulation in houses and related to sustainable built environment, and also solar radiation to heat, which is something an important component in for understanding the temperature of the earth. So when two objects are at different temperatures, the heat is transferred from the hotter object to the colder object. This is something that we already discussed before. The heat transfer can be by conduction or convection, or by radiation, which can take even in the absence of any physical medium between the objects. So the heat transfer, as incorporated into the energy balance, will be that the change of the energy from one body to, or from one system to the other, that is divided by a material, and each region on the system from one side or the other can also be calculated, because it's an enthalpy. It's a loss of enthalpy of a hot body and a gain of enthalpy of the cold body. All right. So this is something that we can keep in mind, because we can also estimate the internal energy of these systems that are joined or divided by some material. So as I explained to you, conduction occurs by a gradient, and this is defined by Fourier's law, that provides an expression for calculating energy flow by conduction. So the flow of heat is a function of the temperature of both the first space and the second space, a heat transfer coefficient, the cross-sectional area of the conductive material, and the length of the conductive material. And here you can see a figure where every component is explained. So the thermal conductivity is particular for each material, as we saw for the specific heat capacity, and it can be described in units of watts per meter per Kelvin, or per unit of temperature. We can also have it as kilojoules per second per meter per unit of temperature, that in this case is Kelvin. You can see again the clear difference among this heat thermal conductivity among materials, right? Where we can observe that there are materials that have a high conductivity, and that is why they're using to transfer to conduct energy. For example, copper, and in a lower extent, aluminum. And there are some other materials that are less prone to conduct energy or thermal conductivity. So in general, we can see that metals tend to be good thermal conductors, while other materials that are poor thermal conductors are useful for thermal insulation. We can also have a similar form of transfer of energy, that is convection. The difference is that in convection there is a force that allows the transfer of the heat. So there's going to be a large scale fluid motion, such as examples include flowing river or aquifer, or the wind blowing. So we need some forces that will allow the transfer of the energy. So convective heat occurs also from the temperature of from hotter to colder, and you can see that the equation is quite similar to the one on conduction. We will have also a coefficient that is called convective heat transfer coefficient, and the main difference here is that the energy is in terms of units of energy per second, but per square meter. So it means that the surface area is the one that is being transferred. The area is considered for the conductivity, for the convection of the heat. So because convection and conduction can occur, are highly interrelated, we better use something that is an equation that is called overall heat transfer, and this is the most efficient or the best way to use or to estimate heat transfer. And this is already used for estimating heat transfer in materials that you can buy for building houses, etc. So for these cases, the equation takes the following form, where we have the change of energy over time equals to heat transfer rate through the wall as Q, and this is equals to the wall area multiplied by the change in temperature, and then divided by the overall thermal resistance. The overall thermal resistance is called R value, and you can buy the materials when you buy insulation materials, they will provide you this R value. So generally you will see materials that are used for ceilings or for walls, and they will provide this R value, and you can estimate the rate of the heat transfer. So for the tutorial, we're gonna have an example where we estimate the transfer of heat either by conduction or convection or with the overall heat transfer. Okay, so you have to keep in mind that you have to read the problem clearly, and what is something very important for you to define which equation to use, so don't get overwhelmed. I think it's important if you look at the units. The units should make sense, because at the end you should have units of energy and units of energy over time, because this is like a rate. Okay, so that will depend which type of equation you need to use. Okay, we're going to start discussing now radiation. Heat transfer by thermal radiation is the third way that an object can warm another. And unlike the previous examples or the previous way of change of energy conduction, radiant energy is transported by electromagnetic waves and does not require a medium to carry the energy. For example, these magnetic waves are the ones that are being transferred from the sun to the earth. And also the earth itself radiates some of the energy. So this is the same case of the electromagnetic phenomena, where radio waves, X-rays and gamma rays can also be emitted. Thermal radiation can be described either by wavelengths or the particle nature of electromagnetic radiation. This in terms of, for instance, discrete photons of energy. All electromagnetic waves travel at the speed of light, so they can be described as a wavelength or the frequency. So the first equation that I'm showing you is a way of explaining the relationship between the wavelength and the frequency with the speed of light. When radiant energy is described in terms of photons, then the relationship is between frequency and energy, and is given by E equals h, which is the Planck's constant, and times the energy of a photon in joules. The equation described before shows that higher frequency, shorter wavelength photons have higher energy content, which makes them potentially more dangerous when living things are exposed to them. So we can use as an example the various gases on climate change that are depleting the ozone layer. So we also have not only gases that are affecting the greenhouse gas effect, but we also have some others that actually are depleting this ozone layer, right? And these ones are important in the range of 0.1 micrometers up to 100 micrometers. So we can see this as in perspective if we look at the portion of the electromagnetic spectrum. Every object emits thermal radiation, and the usual way to describe is to know how much radiation the object emits, and also the characteristic of the wavelength. And everything, when we have a description of the emission, we will always compare it to the theoretical abstraction called a black body. A black body is defined as a perfect emitter as well as a perfect absorber. A perfect emitter is because it radiates more energy per unit of surface area than any real object at the same temperature. And as a perfect absorber, it means that it absorbs all radiation that impinges upon it, that is, nothing is reflected and none is emitted through it. You know that in reality, actual objects do not emit as much radiation as this black body hypothesis, but most of them are close to this theoretical black body. The difference among the radiation an actual object emits related to the amount that is emitted by the black body is called emissivity. And the emissivity it will vary depending on the material. So desert sand can have an emissivity of around 0.9, whereas water can have an emissivity of 0.95. And as a reference, a human body, no matter the pigmentation, will have an emissivity of 0.96. So as I said to you before, the wavelength radiated by a black body will depend on its temperature. And this one is described by the Planck's law, where emissivity power of a black body in watts per square meter per micrometer will be equal to a constant value 1 divided by wavelength, and also will include another constant value and an absolute temperature. Then with this equation we can plot the emissivity at different wavelengths of a spectral of a black body. So you can see the differences in temperature, right? How they describe a different intensity. But how can we interpret this diagram? Well, we can see the area below the curve, and this is equal to the power radiated by the object within the band of the wavelength. So in general, objects with higher temperatures emit more power, and as the figure suggests, their peak intensity occurs at shorter wavelengths. So you know that the solar radiation has some emissivity, right? So extraterrestrial solar radiation just outside the Earth's atmosphere show spectral characteristics that are well approximately to a black body radiation. So for the solar spectrum, the area under the curve is between 0.38 and 0.78 micrometers, and that is 47% of the total area. The previous equation that I showed you and some of the equations that I'm showing you for radiation are just for understanding how energy due to radiation is explained or is described. But for example, the Planck's law is very difficult to manipulate, so that's why we have other two radiation equations that are more straightforward, and one of them is the Stefan Boltzmann law of radiation, which gives us the radiant of energy emitted by the black body with a surface area and absolute temperature. So this is the equation that is more manageable, and the equation that can be used to determine the temperature of a body in the surface. And this is the one that we use actually for determination of the Earth's temperature. The second equation that we can use is the Wiens displacement rule. This one tells us the wavelength at which the spectrum reaches the maximum point, and is defined by a constant value that divided by the temperature. So with this equation we can estimate, for instance, the Earth's spectrum.